So as you know, today's class will be online because of holidays that we have. So hopefully everyone can enjoy the class. Like the other online class that we had, I'm going to record it. This way, those who are not present or you want to review whatever we had in the class, you can access through e-learning. Okay. So I'm going to share the slide. Please let me know if you can see my screen very well and you can hear me well.
Yes, doctor.
Okay. Okay, very good. So we will continue our discussion with what we said about influence line. So far we have learned how to draw influence line using two different methods: quantitative, which was the beginning of our lecture, and qualitative, which was the one that we learned in our previous class. And today's lecture will discuss how we can use this influence line after we drive them. So what's the use of this influence line? This is what we are going to see today. Okay. So in order to um, excuse me. Let me share again. I think something has gone wrong with this. Okay, hopefully everyone can see the screen. Okay, let's assume that we have a beam. Let's assume that we have a beam, and we have drawn the influence line for RA. So we know how to draw it through qualitative approach. We said we remove the support reaction, we impose a unit displacement, and then we look into the displaced shape. So this is going to be the influence line of RA, and the value here equals to 1, it decreases to 0. So this is the influence line of RA. We said we have drawn this for a unit load car that is passing over our bridge from left to right. So now the question is, what if instead of this one unit, we had a car that has 2-point loads representing two wheels of the car, and one of them is larger than the other one. Let's say this one is 10 and this one is 5. In other words, we have a loading condition like this. Let's say the distance of these two also is 1 meter. So if this car pass over this bridge and we want to know how much is the value of RA, how we can use this influence line. So this is something that we want to check on it. Actually, the influence line that you obtain for unit load can be used for any type of loading that your bridge is subjected to. So it doesn't matter that you have obtained it for unit load. If your load is 10 kilonewton, 5 kilonewton, we have 3 loads, 1 load, 5 loads. Again, still this influence line can be used. So how we can use it? Let's say we want to know maximum RA, okay, when this car pass over the bridge. How much is the maximum support reaction when the car pass over the bridge? So if you want to do that, to get that, you need to place your load, which is representing the car, at the locations where the height of your influence line is the largest. So you see the height of the influence line in the beginning equals to 1 and then decreases to 0. So the largest height is here. So if the loads are in the beginning of our influence line, basically they can result in a larger support reaction. So the best option is to put the 10 kilonewton force right at 1. And let's say if the distance of these two is 1 meter and our bridge is 10 meter, assuming, and then the second point goes 1 meter after that, almost, with the intensity of 5. So here, 1 meter after that, you can easily calculate how much is this x from triangle simulation. And the height of the influence line here will be 0.9. So now if you want to calculate the maximum RA, the only thing that you need to do is to multiply the intensity of the load, which is 10, to the height of the influence line, which is 1, and repeat it for the point loads that you have on the bridge. So the second point load is 5, and the height of influence line under the point load is 0.9. And this is going to give you how much is RA under the bridge when on RA when the bridge is subjected to the car. So it is 10 plus 4.5 and equals to 14.5 kilonewton. So what does this mean? This means when this car is passing over the bridge, the maximum RA equals to 14.5 kilonewton. And it happens when the car has been parked right in the beginning of the bridge. Because in this location, the height of the influence line is the largest. Let's see the same bridge, but this time is subjected to, let's say, two different other point loads. Let's assume that one of the point load is 5 and the second one is 10, and the distance between these two is 5 meters. So we want to know that if there is a car carrying a load, something like this, and it passed over our bridge, how much will be RA max, the maximum reaction? So again, you can draw the influence line for RA. We know that it has the value of 1 in the beginning, and it decreases to 0 after 10 meters when we reach to the support. So now we need to decide where we should put our point load. Of course, since we are looking to the maximum value, we need to search for the largest height. So one of the point loads can come and stay on here, right at the 1. So which one of these point loads can be there? If you put 10 here, the other point load will be outside of the bridge, 5, because the distance of these two is 5 meters. So for this case, if you calculate how much is RA, is going to be the value of the intensity of load multiplied by the height of influence line under the load. So it becomes 10. Since this one is not on the bridge, it cannot be counted. So this scenario is giving us maximum RA 10 kilonewton. But we may have a second scenario. In the second scenario, both of these point loads are on our bridge. So we can assume that the 5 kilonewton is here, and the second one, which is 10, comes 5 meters after that here. 5 meters after that. So since the total length of the bridge is 10 meters, and we go to the middle of the bridge, since here is 1, in the middle of the bridge, the height of the influence line becomes 0.5. So for this scenario, RA equals to 10, which is the intensity of the load multiplied by its height of the influence line, plus we have another point load, 5, multiplied by the height of influence line, which is 1. So this results in 5 plus 5, which equals to 10. So for both scenario, we get RA max equals to 10. So that means regardless the car is stopped right in the beginning of the breach and one of the tires only on the span, or both tires comes to the breach and one sits at this place, another one here, then the value of the influence line become, the value of RA become 10. So if you have any question, you can ask. Just open your mic and ask.
Doctor.
Yeah.
Doctor, why 5 multiply with 1?
Because the 5 right now is in this place and the height of influence line in this place is 1. 10 multiplied by 0.5 because we put the 10 kilonewton here because we said it is 5 meter after 5, right? And the height of influence line here is 0.5. So basically you need to multiply the load to the height of influence line where the load is placed. Since the load has been placed here, if the load is 5, 5 multiplied by 1. If the load is here, if it is 10, 10 multiplied by 1. So we investigated two scenarios. One scenario was when we have only one point load, and the second one is out of the breach. So we multiply 10 to 1. Scenario number 2 is both point loads are on the breach. The last tire is here. The first tire comes here, and the distance is 5. So 10 multiplied by this height, which is 0.5, and 5 multiplied by this height, which is 1. Clear?
Yes, doctor.
Okay. So you need to always multiply the value of load, the intensity of load, to the height of influence line to get the value of reaction or shear force or whatever that you need. Let's see one more example. Imagine the same breach. And now we have only 2-point load again. Okay. And both point loads are similar, 5 and 5. And we are interested to know how much is RA max, the maximum of RA, when this car is passing over the breach. So RA max is needed when the car is passing over the breach. So the first thing that we need to do is to draw the influence line for RA. So this is the influence line for RA. It is 1 at the beginning and 0 at the end. So we got this one. Now we should decide where to put our load that can give that have the largest height of influence line. So we can investigate basically two scenarios again. Scenario number 1 is when the car has stopped right in the beginning of the breach. So if it is in the beginning of the breach, only one of the tire is here, the other tire is outside. Let's say the distance between these two is 3 meters, for example. So we have 5 here and another 5 here. So this is one of the scenarios. Another scenario that we can investigate is the case when the car has come in. One of the tire is there, one of the tire is here. So this is our car, and we have 1 5 kilonewton here and another 5 kilonewton here. So the distance between these two also is 3 meters. So for the scenario number 1, if you want to calculate RA, you just need to multiply the force, which is 5, 1. The other force is not counted because there is no any breach under the tire. So it becomes 5 kilonewton. This is for scenario number 1. Scenario number 2 has 2-point load. So RA is going to be this 5 multiplied by this height, which is 1. So 5 multiplied by 1. And then this 5 multiplied by this height. So if the total length of the bridge is 10 meters and this one is 1, this height will be 0.7. After 3 meters, you go based on the triangle similarity. So the second 5 should be multiplied by this height, which is 0.7. So this gives you 5 plus 3.5, which is 8.5. So you can see this scenario is more critical, and the maximum RA equals to 8.5. So when you are having a breach, you need to examine different scenarios if you are looking into the maximum values or minimum values. This is something that we need to examine it by placing the car or the load in different locations and calculating the worst case scenario. This example that I just gave to you is for the time that your bridge is subjected to point load. But there are times that our bridge is subjected to uniform load. One of the uniform load that all bridges are carrying is their self-weight. You know that you have a beam made of concrete, and this beam has its own cross-section, and it distributes the load, the self-weight of the beam uniformly all over the structure. So this is one of the uniform load that can excite our structure, our bridge. Or there are times that something that passes over the bridge is uniform load. For example, you have seen these excavators. These excavators, they have this chain type moving system. So when they are moving over our bridge, they almost uniformly exciting this bridge. The length of this can be anything, let's say 4 meters, and they may have a different intensity, let's say 20 kilonewton per meter, with a length of 4 meters. So they pass over the bridge. Self-weight is always there, doesn't move, but this type of vehicle can easily pass over our bridge, and they can initiate axial force, shear force, and anything inside our structure. So we need to know whether our influence line still can be used for uniform load or not. So the answer is yes. If you want to know, let's say, what is maximum RA for a uniform load, a moving uniform load that pass over our bridge, so we can calculate it the way that I explained. Let's say we have this 4 meter length with 10 kilonewton per meter load, which is passing over our bridge from left to right, and the bridge is also 10 meter length. And we are interested to know how much is RA max if this load that represents this vehicle pass over our bridge. So if you want to calculate RA max, first you need to draw the influence line. You need to draw the influence line, and the influence line is similar to what I said to you, 1 here and 0 here. Okay, please wait for a while. I need to deal with something. I will come back, okay? Okay, sorry, I'm back. So I was talking about how we can deal with uniform load and obtain the maximum reaction, for example, in this case. So we have here this 4 kilonewton, 4 meter length uniform load that is passing over our bridge, and we want to know how much is RA max. So we draw first the influence line for the RA, and then in the second step, we need to decide where to put the load. Similar to what I said for point load, you need to put the load in the place that has the largest height. So the largest height for RA is in the beginning of its diagram. So that 10 kilonewton per meter with the length of 4 meter should be placed in the beginning of our graph, okay? Because here we have a larger height. And the length is given to us from here to here, 4 meter. So if the total length again is 10 meter, this one should be around 0.6. So when it comes to point load, we multiply the intensity of the load to the height to get the reaction. But for uniform load, you need to multiply the intensity of your load to the area to get the reaction. So under uniform load, RA max is going to be 10 multiplied by this A. The area which is under your uniform load. So you know how to calculate that. It is a trapezoidal shape, so it is 1 plus 0.6 multiplied by 4 divided by 2. So this one becomes 1.6 divided by 4 becomes 0.8 multiplied by 4, 3.2. So it's around 32 almost, if I'm not mistaken. So this is going to be the maximum support reaction due to the uniform load of 10 kilonewton per meter. What if we want to include the effect of self-weight? So let's say it is given to us that the self-weight of the beam is 2 kilonewton per meter. When we say self-weight, that means it is all over the span. It applies from the beginning until the end of the span. So if you want to calculate the reaction due to the self-weight, you do the same method that I explained for moving load. That means first we draw the influence line for RA, and then we need to place the self-weight on top of our structure. But now we don't need to decide where we should put it because self-weight is always all over the span. So it starts from the beginning of the span until the end of the span, and it doesn't move. So this is the influence line of RA. Here is 1, here is 0. And as we said, if we want to calculate RA, in this case, we need to multiply the intensity of load to the area, which is this A, from beginning until the end. So it's going to be 2 multiplied by A, and that equals to 2 multiplied by 10, which is the length of this triangle, multiplied by its height, which is 1, and divided by 2. So 20 divided by 2 is 10 kilonewton. So that means under the self-weight, the reaction that is generated here is around 10. Okay, any question? Yes?
Doctor, what it means self-work 2 kilonewton? Actually,
Self-weight is the weight of the beam of the structure. So let's say you have a bridge, and normally the bridge, if it is 10 meter, let's say the width is around 0.2, the height is 0.6. So this beam has its weight because it is having concrete inside, right? So this weight generates also reaction here when you place it on the structure. And this 2 kilonewton that I put here is meaning that 1 meter of the bridge equals to 2 kilonewton as a uniform load due to the self-weight. Clear?
okay, doctor.
Okay. So based on this explanation, now you know that if you have point load should be multiple to the height to get the value. Doesn't matter how many point load you have. What is the intensity of point load? Doesn't matter. You just multiply the height of influence line to the place that the point load is there. If you have uniform load, you are going to multiply the intensity of uniform load to the area which is covered by the uniform load. This way you can get the values. Now let's make it a little bit more complete. What if our bridge is subjected to not only point load, but also uniform load at the same time? So let's say we have a bridge with a length of 10 meters, and we want to calculate our A max when the bridge is subjected to 3 types of load. One is a uniform load with 2 meter length. Let's say it is 2 meter. And, oops. And 2 meter, and let's say the intensity is 5 kilonewton per meter. And let's say we have also a point load of 10 kilonewton, which is moving. So these two are moving. And then let's say we have also self-weight, a self-weight of the bridge, which is 1 kilonewton per meter. So we want to know if these 3 loads are simultaneously applied to the bridge, how much is our A max? So this is something that we need to solve. So again, the first thing that we need to do is to draw the influence line. So we draw the influence line, and we know the influence line starts from 1 and goes to 0. So this is influence line of RA. The second step is to decide where we should put the load to give us the maximum RA. Let's just start with the self-weight, because as we said, self-weight doesn't move and they are all over the span. So this is going to be our self-weight, starting from beginning of the bridge and spans to the end. And intensity is 1 kilonewton per meter. So this is the self-weight. Now it comes to the point load. Where should I put this point load to get the maximum response? We said we should put it in the place that the height of influence line is largest. So if I put it in the beginning of the graph, I will get the largest value, because here the height is 1 and it goes to the right side, that height decreases to 0. So my point load should be right in the beginning of the span. How about the uniform load? The moving uniform load also should be placed in the location where the area is giving the largest area. Again, that should be in the beginning of our beam or slab, because it's the area in which the height is the largest. So that one also should be placed here with the intensity of 5 millimeter. So that one was 10, and this one is 5. And we know that the length of this is 2 meter. So here I should know how much is the height, because at the end, this area is the area which is covered by the load. And from here to here is this 2 meter, which is given to me. So if the total length is 10 meter, if you go 2 meter that side, the height of the influence line becomes 0.8. So now I can calculate the value of RA, because I have realized where should I put the load to get the maximum values. So RA, first, due to the self-weight, is nothing but the force, which is 1, multiplied by the total area underneath, because the load is covering from beginning until the end of the span. So we should multiply it to this A, So from there, I can say we have 1 multiplied by 10 multiplied by 1 divided by 2, which equals to 5. So the self-weight gives us 5 kilonewton as a reaction in RA. And then we have point load, which is moving point load. So we just need to multiply the intensity of the load to the height of influence line, which is 10 multiplied by intensity under the point load, which is 1, equals to 10 kilonewton. And then we have moving uniform load. So for uniform load, we multiply the intensity of load, which is 5, to the area underneath. This is, let's say, A2 to A2. And that is 5 multiplied by 1 plus 0.8 multiplied by 2 divided by 2. So this one can be 1.8 multiplied by 5 is 9. So the RA max equals to summation of these three effects. So we have 5 plus 10 plus 9. So it's going to be 24 kilonewton. So that means if this bridge is subjected to the 2.22 loads, which is moving, and one load which is constantly all over the bridge due to the self-weight, the maximum reaction that we can get from our for our support reaction is 24 kilonewton. So this seems to be right now very easy, but we have cases that decision on the location of the point load and uniform load that moves is needing a little bit of trial and error, and it is not easily can be decided where to put the load. And I will show you one example here. Let's say we have a bridge similar to what you see here. And for this bridge, we are interested to calculate RB max under these loads. We have a moving load. We have a moving load. Let's say the length is given to us 5 meters. Intensity is 10 kilonewton per meter. We have a single point load. Intensity is 10. And this one is moving. And let's say we have self-weight of 2 kilonewton per meter. So anywhere you hear about self-weight, that means all over the span. Okay? So now we want to know if we have two moving loads. One is 10 with 5 meter length, and another one is 10 point load, and we have this self-weight. How much will be the maximum RB? Okay, so the first thing that we need to do is to draw the influence line of RB. So we said we need to remove the support. We need to remove the support and then impose a unit displacement and look into the displaced shape. So if you poke this one up from here, push it up, this location remain in this place. And since we have a hinge over there, if you pull this one up, the hinge also can go up if this allows. Since we have also here allowed a rotation, so this point also can go up. In other words, the deflected shape will look like this one, in which here the height is 1, which is the location of RB. Here we have 0, and here also we have 0. And you can easily calculate this one if the distances is given to you. So let's assume that everything is 5 meters here. So in that case, you can easily calculate this one is x over 1 equals to 10 divided by 5. So basically, this x equals to 2. So this is the influence line of RB. Any question?
Doctor,
Yeah.
the influence line, the
Okay.
highest point should be on B, right? Not to hinge.
No. It can be larger if the condition arises. The only thing that you need to know is that only in the place that you impose the displacement equals to units. So you need to calculate how much it will be in other places. It can be larger than 1 or it can be smaller than 1. Any other question? Okay, now that we have our influence line in our hand, which is this one, okay, we need to decide where we should put the loads. I think Shazwana, please make your mic close. And anyone else that his mic is open. Okay, so let's see where we should put the load. Let's just start with the self-weight, which we said always it is all over the span. So it starts from here and goes until the end of the span. Okay, so the intensity is 2 kilonewton per meter. And we know that if you want to calculate RB due to the self-weight, we need to multiply these two to the complete area under the load, which is from beginning until the end of the influence line. Now, where should I put the 10 kilonewton, the point load? So if you look at the height, you will see the largest height that we have is these two. So the point load should be right here to give us the largest value of RB. Now it comes to the second point load, so second moving load, which is uniform. Where should I put it? I can put it in the right side here, or I can put it in the left side. So to make my decision final, we need to see which of these two areas are larger, because we are looking in RB max. So the larger is the area, basically the larger will be the result of this reaction. So you can easily see that this area, which I call it, let's say A2, is 5 multiplied by 210 divided by 2 is 5. How about this area? Is 2 plus 1 is 3 multiplied by 5, 15 divided by 2, 7.5. So A1 is 7.5 meters square and A2 is 5. So this means that I need to put the load on the left side of the hinge. This way I can get a larger reaction. So it comes here. So now I can calculate the reaction. So RB, the reaction comes from three sources: self-weight, which is here. So we have 2 kilonewton multiplied by this triangle, which is 15 multiplied by 2 divided by 2. So this is 30 kilonewton from self-weight. The second one, which is a moving point load, it is 10 multiplied by 2, which is the height of influence line, gives us 20 kilonewton. And the third, which is coming from this load, is 10, which is the height of the value of force multiplied by the area, which is A1, and it's 10 multiplied by 7.5, which is going to be 75. So RB max is the summation of these three loads, meaning 30, 20, and 75. So which is 125 kilonewton. So we obtain right now how much is there? The value of RB max. Okay. Any question? Okay, let's make it a little bit more complicated and see if we can this time calculate how much is RA max. RA max. So if you want to calculate RA max, first we need to draw the influence line of RA, and from there we can decide on the location of the loads and see where is the best place to put our load. Okay, so I draw this one. How much? I want to know how much is RA max. The loads are the same, but the reaction will be right now RA. Okay, so let's draw first the influence line. So if you want to draw the influence line, we need to impose a unit displacement to this location. So we apply unit displacement over there and see whether the structure can have deformation in the right side or not. So if you pull this one up, this one cannot go up and down, but it can rotate. So it is allowed to rotate only if this portion also can rotate. Since there is a hinge over there, and we have also a pin support, if you pull this one up, this can go down. So basically what happens is that we are going to have a deflection similar to what you see here. So this is going to be the influence line of RA. And how much is this one? From here to here? Since this distance is 5, and this distance also is 5, so the influence line equals to, the height equals to -1. Don't forget this is negative. Okay? So now that we have our A in hand, we need to decide on the location of our loads. So let me just draw it again down here and then see where we should put all those loads to get the maximum of RA. So here is 1, here is -1. Let's start again with the easiest part, which is self-weight. So the self-weight will be placed from beginning until the end of the span because it is all over the span and the intensity is 2 kilonewton per meter. Okay, now where should I put this 10 kilonewton? We have -1 here and we have +1 here. If in the exam you will be asked to do this, either we tell you that find maximum RA positive or compression or tension. If it was not given, then you need to examine it and see the maximum is obtained for negative can be obtained or the maximum positive of RA can be achieved and which one is the largest. So in this example, I will calculate 2 cases. That means RA positive max and RA negative max. Because RA can be under tension or can be compression. So for both cases, we need to do the calculation. So first, let's start with RA positive and see what we can get. So for RA positive, since we are looking to the positive value, we put our point load in a positive side of our graph. Since here is +1 and the largest value is here, so we put it there. And then we need to decide on our next load, which is the 10 kilonewton. So for 10 kilonewton also, if you are looking into the positive value, so you should put it on a positive side of the graph. And this is exactly here. So we have here this 10 kilonewton. And from here to here also, which is under the load, is 5 meter. 5 meter. So we need to calculate this area. 5 multiplied by 1 is 2.5 divided by 2. This area is also needed because although it is a negative area, because our self-weight is spanning all over the bridge, so when we want to calculate the reaction due to the self-weight, we need to take into account the negative area also. And it's given to us from here to here is 10 meter. So 10 multiplied by negative 1 divided by 2, the area equals to negative 5. So if you want to calculate RA, now we have everything in our hand. So from self-weight, we have these two multiplied by two areas that we have, 2.5 plus negative 5. Don't forget, if the area is negative or if the height is negative, you need to put negative inside your calculations. So this is going to be negative 2.5 multiplied by 2, it becomes negative 5. So this is due to the self-weight. Another RA is due to the point load, which is 10 multiplied by 1. It becomes positive 10. And another RA is due to the uniform moving load. So we need to calculate it based on the area. 10 multiplied by 2.5, which is the area, it becomes 25. So if you sum up all, it's going to be negative 5 plus 10 plus 25. So it is 35 minus 5, it's become 30 kilometers. So this is the positive value that RA can have. When it comes to negative value, then this is the time that we need to move our load to the negative side of the graph. To the negative side of the graph. Obviously, the point load that can move should be here with the intensity of 10, because this height is the largest height. But for the second uniform load, the second moving load, this one, is not as easy as we decided to put it right here. Of course, one option is to put that 10 to this side and calculate this area and multiply it to the intensity, right? This is one option. But we have also another option that may give us a little bit larger area. So, and that's the time that you put it right in the middle. That means 2.5 here, 2.5 here, and then you have this black area underneath. So you need to see which one is giving you a largest area. The triangle in the right side, this triangle. So if you calculate the area is negative 5 multiplied by negative 1 multiplied by 5 divided by 2, it gives you negative 2.5. And then for this one, which is 2.5 meter this side and 2.5 meter the other side, first you need to calculate how much is the height. Okay, so this x has to be calculated, which is going to be 0.5 because we are right in the middle, so negative 0.5. So you have right now this area to calculate. This is the area that you need to calculate. Here is negative 0.5, negative 0.5, negative 1, and here is 2.5 and 2.5. And your load right is in the middle of the span with the intensity of 10. So this area you can easily calculate it. Negative 1 plus this one, it becomes 1.5. 1.5, you need to multiply it 1.5 to 2.5. 1.5 multiplied by 2.5 and then divided by 2. So you get 1.87 and then multiplied by 2 because you have two areas. So the total area, it becomes 3.75. So you see this case, is giving us a larger area compared to this case. So this scenario is not producing larger value compared to this scenario. So now we have one point load right in the middle, our uniformly distributed load that can move again in the middle of the span, and we have the uniformly distributed load. So if you want to calculate RA negative, the value that comes from the uniform load is the same because it is always all over the span, so it doesn't matter. It is positive or negative, it is always the same value. And then we have another RA, which is the point load, so 10 multiplied by -1, which gives us -10. And RA from uniformly moving load, this one, is 10 multiplied by -3.75, which is 37.5 negative. So RA negative max, this one was RA positive. RA negative max equals to 37.5, 10, and 5. So 15 is -42.5. So you see the negative value is much larger than the positive value. That means if you want to design this support for these loads, you need to consider two cases. One, when it is under compression, the value is given to us 30, and another time when it is under tension. So for both cases has to be checked and make sure that the support is functioning correctly. Any questions so far? Any question?
Doctor,
Okay.
can you explain again why we need a positive and negative RA?
Okay. You know, in some cases, the reactions that we calculate under the moving load can have positive value or negative value. Just consider the previous case that we had RB. We said RB's influence line looks like this. So we have one here and two here. So in this case, wherever you put the load, wherever you put, RB become always positive. But when you draw the influence line of RA, you see RB also can be negative, and depends where you put your load. If your loads are in the beginning of the span, RA is positive. But if your car come and stay here, for example, and this is the time that RA is going to be pulled, and you need to design that RA for the negative sign as well. So in the exam, sometimes we directly mention to you that calculate positive bending moment, calculate negative maximum bending moment, or positive maximum support reaction, or negative. So this is straightforward if you have always positive value. But if your load can make the reaction sometimes positive, sometimes negative, then you need to calculate both to see which one of these two is the largest. The largest value is positive or the largest value is negative. Clear?
Clear, Doctor.
Okay. Okay, the example that we solved so far is related all to support reaction. So we can also draw the calculations, make the calculations for shear force and bending moment as well. So this is what we can do in our next example. Let's say we have been given a beam like the one that you see here. Okay. Let's say the distance between the spans is 10 and 5 and 5. Okay. And let's say we have been asked to calculate maximum shear force at point B under the following loads. We have moving load of 10 and 5 with the distance of 2.5 meter. We have a uniform load of 5 kilonewton, and from beginning until the end is 5 meter. And then we have a uniformly distributed self-weight of 1 kilonewton per meter. So we want to know, again, this VB that we don't know can be positive or negative. How much is the maximum of this shear force if these point loads pass over the bridge and together with this uniform load and this self-weight? Okay, so this is what we want to do. So in order to deal with this, again, we need to draw the influence line first. Influence line for shear force. We said for shear force, we need to add one internal roller and move the left side down and right side up and look into the deformed shape. And the deformed shape is basically gives us the influence line for that shear force in that location. So if you look at this beam, the left side of this beam is connected to a rod which is fixed by 2 supports. So if I want to push this one down, either it should bend or this side should go up. But since it is fixed to this area, so that means the support cannot allow the rod to rotate. Therefore, the left side cannot move. And since we don't allow it to bend, it is either rotating or going up and down. So the left side cannot have any type of movement. But the right side, we have a pin support over there, and this pin support allow rotation. So if I push that one up, basically it can rotate around this support, and from there I can get the influence line. So if I want to draw the influence line, it's going to look like this. Okay, it seems that my laptop, okay. Okay, the influence line is going to look like this. Okay, and we said the deformation that we apply is unit. So it goes up only because, as I said, the left side doesn't allow you to move. So this is the influence line for shear force at point B. And the leg is given to us from here to here to be 5 meters. Okay, so now we need to decide where we should put our loads. So uniform load, again, is all over the span. And the intensity of this uniform load is 1 kilonewton per meter. So we need to decide for the other 2-point loads where we should put them. Obviously, the largest height is in the beginning of here. So I can put the 10 here, and 2.5 meter after that, which goes to the middle of the span, I can put the 5. So the height here, which is 2.5 meter after the 1, is going to be 0.5 because it is the middle of the span, and from here to here also we have this 2.5. So that one also was decided, and we have left only one more, and that is the moving uniform load. Since the length is 5 meter, which is all over the span, so it should be also placed right here from beginning until the end of the influence line, and intensity is 5. So now if I want to calculate VB max, we are going to have 1 kilonewton multiplied by the area of influence line, which is 5 multiplied by 1 divided by 2, which is 2.5. So this is the value that comes from self-weight, the self-weight. And then we have also a value that comes from the point load. We have that 10, which multiples to the height, which is 1. And then we have 5, which multiplies to the height, which is 0.5. And this is going to give us 10 plus 2.5 is 12.5. Okay, so this is from the uniform, this is coming from the point loads over there. And the last one is the uniform load, which moves. So that one is going to be 5, also multiplied by the area under that load, which is the complete area up here, because the length of the load is 5, and the influence line also gives us a 5-meter length. So it's going to be 5 multiplied by 2 divided by 2, which is 2.5, the area. This is the area. So this one also result is 12.5. So VB, the maximum VB is 12.5 plus 20.5 plus 2.5, which equals to 27.5. So again, in this case, you can see VB is always positive, the shear force. And this is because of the shape of the influence line. You may have cases, you may have influence line like this shape. So in that case, you need to decide where to put these values to get the positive VB and negative VB, like the example that we solved in the previous case. Any question? Any question? Okay,
No,
let's see one more example. And then after that, we can have some rest and come back again. Okay, so let me delete this. So in this example, we look into the influence line for bending moment, and we want to see how we can calculate the maximum bending moment. Again, bending moment can have maximum positive, or they can have maximum negative. So we need to check and see which one is the governing one. So let's say we have 5 meters here, 5 meters here, and 2 meters here. And we are interested to know about MA, the maximum bending moment that can happen there. Still, we don't know if it's going to be positive or negative until we draw the influence line and we apply the forces to see MA is always positive, or we can take the negative value. And let's assume that we have only one point load. The intensity is, let's say, 10. We have a uniform distributed load. Let's say the intensity of this load is 5, and the length is given to us. Let's say the length is given to us 10 meters. Okay, and then we have also self-weight, and the self-weight is 1 kilonewton per meter, and the length is always all over your span. Okay, so under these 3 loads, we want to know how much is MA max. MA max. The positive or negative sign can be only decided after we select the location of the load and see whether it can take positive and negative or not. So first thing first, we need to draw the influence line for MA. If you remember, we said if we want to draw the influence line for bending moment, we need to put one internal hinge in that location, and then apply a clockwise rotation to the right side and counterclockwise rotation to the left side. And then look into the deformed shape. The deformed shape is the influence line. So let me draw that one. Okay, this is the beam, and this is our internal hinge. So if you look carefully, the moment that you apply this rotation to the right side, left side is support and nothing is there. So we need to focus on the right side. So the moment that you apply this rotation here, it wants to rotate the beam to go down, and it can go down only if this hinge allow it. Okay, since we have a hinge here, yes, it can go down. And if there was support here, of course, there was no way that this one can move. But since there is no support, so the moment that this one goes down, the other side can go up. So it can rotate along this support. Therefore, our deformed shape, after we apply that rotation, is going to look like this. So this is the influence line for MA. And we said we rotated 1 radian. So if the length is 5 meters from here to here, okay, it's 5 meters. So this height will be also 5, because from mathematics we know 5 multiplied by 1 radian equals to the height in front of the angle. And if you have 5 here, sorry, this one is 2 meters. So you can calculate this much, this one. So this one is x over 5 should equal to 2 over 5. So it's 10 divided by 5 equals to 2. So here we have negative 5. Here we have positive 2. So if you look at this diagram, you definitely know that you will have negative areas and you have positive areas. So depending on the condition of your loading, your bending moment can have maximum positive and maximum negative. Okay? So let's put the load on the structure and see what we can get. First thing is the self-weight, which is coming from beginning until the end of the diagram. So the intensity of this self-weight is 1 kilonewton per meter, and it is applied all over the span. The second one is the point load, that 10. So if you are looking into MA negative, we should put it in the area that has the largest negative height of influence line. So that area is right on top of the 5 kilonewton, which is here. So it comes here. We have this 10. And then we have this uniformly distributed moving load with the height of 10. Since the length is 10 meters, so if you look into the maximum negative, that means it's going to cover from beginning until the end of the span. So it should be placed right here. This way, it can generate for us only negative bending moment. Okay? So here also the intensity is 5. So this loading condition gives us the maximum negative bending moment. So we need to calculate the areas. The area for this one, you can easily calculate it. It is 10 multiplied by 5, 50 divided by 2, negative 25. So this is the area. And we have another area here, which is 2 multiplied by 2, 4 divided by 2 equals to 2. So this is A2, and this one is A1. So this area, don't forget, it is negative, and the other area is positive. It is always should be taken into account. So if you want to calculate the effect of self-weight, so this 1 kilonewton per meter should be multiplied to A1 plus A2. 2 areas that we have, because it is from beginning until the end of the span. So if you put here negative 25 plus 2, so you have negative 23. So the area totally become negative 23. Multiplied by 1 become negative 23.
Doctor,
Yeah,
The A1 should be 12.5, right?
10 multiplied by 5 divided by 2.
10.
The length from here to here is 10 meters. Multiplied by height, which is 5. 10 multiplied by 5 is 50.
Okay,
50 divided by 2 is 25. Correct?
Okay.
Okay. So we have this one, negative 23. And then we can calculate right now the effect of point load. So we have there 10. We should be multiple to our height, which is negative 5. So that gives you negative 50. Okay? And then we have also this moving uniform load, which is placed from beginning until 10 meter because the length is 10 meter. So that one is going to be 5 multiplied by the area, which is A1, is going to be 5 multiplied by 25, negative 125. So if you sum up all, it's going to be the total MA 175, 198, if I'm not mistaken, 198 kilonewton meter. So this is a negative value. And if they ask you to calculate MA positive, MA positive, you need to see whether the bending moment can go positive or not. So in that case, the one that comes from uniformly distributed load, I mean the self weight, is there. So we can't change it because this doesn't move. And it completely covered the span from beginning to end. So we have that negative 23 over there from the self weight, which is there. So we have a negative value. We should see whether in total this negative can become positive or not. So if you want to make the bending moment positive, obviously this 10 that before this was in the negative side should be shifted to the positive side, should come here. So this is 10, right? So we have positive 10 multiplied by 2. This one can give us around 20 kilonewton. Now we left with this moving load, the 5. So this one also you should shift it to this side, and it's going to cover from here to here. So 8 meter of the span is going to be covered with negative sign. This is going to be the 8 meter. And 2 meter of the span is going to be covered with positive sign. So you need to calculate the area, which is 5 meter plus 3 meter. So this is 3 plus 5. So you can do that calculation and put it here. Obviously, since we have a larger negative area, that one also become negative. So in general, if you sum up at the end, you will see that in worst case scenario where that everything is in positive side of the diagram, still the bending moment is negative. So for this case, the bending moment is always negative, and the largest is this 198. As I said, it is depending on the condition of your beam and the location that you are calculating. Sometimes you may have also a positive bending moment, and you need to investigate case by case. Okay, any question?
So, doctor,
Yeah.
we have to calculate both positive and negative.
If in the exam we didn't tell you that we want positive or negative, yes, but often we inform you that calculate the maximum negative bending moment, for example. Then you just come and put it in negative side.
Okay.
But for
if-
real design, if you are designing a bridge, then both should be investigated. Any other question? Okay, if you don't have any questions, so I think we can go to 10 to 15 minutes rest. So around 3:40, 3:45, we can come back and continue.
ما تحول عشان ما نيجي هنيجي سامة الزبدة ما تنسى الساعة 7 ها؟ الحين 6:30 اللي اسمع عند الحين بسألك هسي مش بدنا اثنين في السكن؟ بالظبط
Okay, welcome back. Let's see some of the solved example. These are normally the questions given to our student during past semester for test or final exam. And now we can check on the result that has been solved. um, so here it's a question given to for test 2, if I'm not mistaken, written up there. After drawing the influence line for RA, RC, RD, and VC, so the question is asking how much is RC max and VC max if this bridge is subjected to this moving load. We have 2-point load, 10, 5, and distance is 1 meter, and the self-weight, 15 kilonewton. So for VC, this is our influence line. So here you can see it hasn't been mentioned VC positive or VC negative, because if you draw the VC's influence line, you will see it's always negative. So under normal circumstances, it becomes positive. So if you want to get a maximum, you have 2 options to place the point load. One option is to put the point load 110 here and 5 after that, with a distance of 1 meter. So if you make this condition happen, you have only 10 multiplied by 1, and you get negative 10 from your point load. The second case is the one that has been written there. That means 5 is here and 10 is here. So in that case, since the distance is given to you 1, height here become negative 0.75. So you have 10 multiplied by negative 0.75, 5 multiplied by 1. It's going to be 12.5, which is much larger than this, negative 12.5. If you compare it with negative 10, so this case covers. So this is why we have this condition. And then the uniform load also will be always all over the span. So This is what you see from our calculation here. For RC max, also we know that the point load should be always at the largest height. So here we have 1, here we have 1.2. So the distance also is given to us from here 1 meter. So 10 goes to the highest height and 5 goes to 1. So 10 multiplied by 1.2, 5 multiplied by 1 comes from the point load. And you can calculate the area, multiplied by 15. It gives the self weight. Summation of these two result in this value. So for RC also, if you look carefully, you see the areas is always positive. Therefore, we don't have negative value for the reactions. So we can see another example also be solved. These examples have been already uploaded inside the e-learning, so you can access to it. The second example also is a two-span beam. You can see 6 meter, 4 meter, and 10 meter, 2 meter, 2 meter. But in this case, we have cantilever from both sides of our bridge. And it is subjected to self-weight, 15 kilonewton per meter, and 2-point load, 1.5 and 1.1. Distance is given to us 3 meter. So you need to draw first RV, RD, RE, VC, and also ME. And the question is asking to calculate how much is V max and M max. That is the bending moment at point E, how much is the maximum, and the shear force at point C, how much is the maximum. So for this case of BC, you have positive area and we have negative area. You can see the positive area, the height is 1/3, the negative is -1. From here to here also is given to you 6, and from here to here is 2. So if we calculate this area, it becomes -3. If we calculate this area, 2 multiplied by 1/3 divided by 6 is going to be 2/6 or 1/3. So this area is significantly smaller than this area. And obviously, the VC value is hardly unlikely to become positive. But you need to point load and find the point load and see what you get. So if you want to see the value of VC, the maximum, again, you have two options. Option number one is to put the point load, one here, 5, and another one, 1 meter after that. So in that case, you have 5 multiplied by -1 and 1 multiplied by 0. So you get -5. Option number 2 is to put 1 right here and 5 should go 3 meter before. So in that case, you have to calculate what is the height here. Since the length is 6 meters, the height becomes half of it, -0.5. So you have 5 multiplied by -0.5, 1 multiplied by -1. So it becomes -2.5 plus -1, -3.5. So between these two scenarios, this scenario is the governing one. So that's why 1 goes after and 5 is right at the place the height is 1. So this is the location of the point load. Uniform load is all over the span. And for this case, you get -45. If you want to calculate the positive, then you need to bring these two and put it this side and see whether you can get a positive sign or not. But since the values are small, even if you multiply 5 to 1/3, it becomes 5/3, which is much smaller than this value. So we become always negative. And the largest negative is the value that you can see here. Okay, so this is just an example. You can look at it with care. And if you have any question, then we can discuss it. Any question? With this example, we can close the story of influence line. So we can move to our new topic, which is about plastic analysis. If you have any question regarding influence line, you can ask during our next class when we have face-to-face. So try to see you can solve these examples by yourself without looking into the answer or not. Any question? Yes, if you have question, you can open your mic and you can ask. Okay, so if you don't have any question, we can move to plastic analysis. Yes. Question?
Doctor, it's mistake. Sorry.
Okay. So I will share with you the slide that I have uploaded for plastic analysis, and then we can see my screen. So let's go here. Let me close this one first. Okay. Okay, hopefully you can see. As I mentioned, the content of the note that I have uploaded in the internet for many cases is more than whatever you need. And you need to just look into the presentation and whatever I prepare in the class for you. So the part which is extra, you can just do self-study. And only the part that I highlight is the part that is coming for the exam. Okay, so we go to the plastic analysis. All the techniques that so far you have learned for analysis of a structure like moment distribution, slope deflection, virtual force method, these are all applicable to linear structure. And if the internal linear legend, then this is the time that we need to look into a new technique that can analyze our structure. So this is what we are going to basically discuss after this. The difference between plastic analysis and elastic analysis is that in the elastic analysis, we assume that all materials that we are using, the stress inside them remain in the elastic zone. They don't reach to yield yet. But in the plastic analysis, we assume that they have passed the yield, and we want to see whether they are stable, what is the bending moment, and how we can analyze them basically. Normally, plastic analysis results in a smaller size for our beam and column, and it's more economical. But there should be some kind of concern about the safety of our structure, similar to what we do for elastic analysis. So we need to take care of bending moment and make sure that our structure, if it wants to fail, has a safety factor. And nowadays, some codes are adopting plastic analysis for the design. For example, if you design for concrete, basically you assume that your enclosing bar reaches to yield and your concrete also reaches to its ultimate capacity at the ultimate stage of loading. So you factor your load, you increase the load, and then you also consider yield strength inside your analysis. So you're kind of doing plastic analysis, although your method of analysis for the structure might be elastic, but the design is almost plastic. So what are these plastic and elastic means? Try to look into the diagram that I have down here. This diagram is the stress strain curve for steel. If you have a rod and you put it inside tensile string machine and you apply a force to that, you will see that little by little, your bar's length is going to enlarge, and that's what we call it elongation. And if you calculate that elongation and divide it to the original length of your bar, then you can get a parameter that we call it strain. So this is delta L, elongation divided by the length, which is L. And if you divide the force that you have applied to the cross-section area of your bar, you get a stress. So if you plot this stress against stress for a steel, for a mild steel, so this is what you can get. In the beginning, there is a linear relationship between the stress and the strain, and this is what we call it modulus of elasticity of steel. The ratio of sigma over epsilon, which is stress over strain. So until this relationship is linear, we have elastic analysis, and all those moment distribution and slope deflection method are valid until this stage. However, if you increase the force a little bit more, you increase this T, little by little, the material is going to show an increase in the elongation. It is going to show increase in the elongation, but without increase in the stress. So stress remains the same, but the bar is going to get long. And at that moment, we have yield. So this is the yielding stage. So when the yielding pass, we have another condition that we call it strain hardening. So in strain hardening, the bar again gain resistance, and stress is going to increase until a rupture occurs inside our material. So this curve is basically a mild steel stress strain curve. And when we go beyond the yield is the time that we are talking about plastic analysis or plastic design. So let's go and see what happens to our beam little by little when the force is increasing. So try to assume that we have this beam subjected to a point load right in the middle of the span. And due to this, we are going to have a bending moment inside our beam, which is maximum occurs right under the point load. Let's assume that the cross section of this beam is something like this. So it can have a rectangular, triangular, circular, any shape. In the beginning, when the load intensity is small, this P is small. So if you look into the stress of the section, the stress block is going to look like the one that you see in my slide. So we have a triangle shape. On top, we have compression on this zone. At the bottom, we have tension. So this compression and tension are in balance, and the balance is there. And you can see that we have a line that passed through this joint that we call it natural axis. So the more you get far from the neutral axis, the larger become the stress inside the fibers. And if you come to the center of your section, basically stress will be almost zero over there. So you can increase the force and make this force to get a little bit larger. If you do so, you will see that little by little, some of the fibers that is inside your section, their stress reaches to the yield stress. And the other fibers are still below the yield stress. So the stress block is going to look like the one that you see here. But still, we haven't entered to the plastic zone. And if you increase that P inside your beam larger and make it bigger, little by little, more and more fibers are going to reach to the yield. And the block more and more is going to look like a rectangle shape. There is a point in which all the fibers inside your section, they have reached to the yield stress. So this is the moment that we call it plastic moment. And there is a plastic hinge also formed inside your beam, right at the place that the bending moment is maximum, meaning here. So at this time, the bending moment inside your section equals to MP. And this is the largest bending moment that your section can carry. So when you reach to this stage, the relationship between section modulus and the yield stress is going to change. Before this, we could always calculate the bending moment from the stress and section modulus. You have this equation, sigma, which is the stress, equals to bending moment divided by section modulus. And this section modulus is defined as moment of inertia divided by y, which is the distance of the fiber, which is the distance of the fiber to the neutral axis. So when this m isn't still reached to mp, this equation is always valid, and you can always relate the bending moment to the stress and to the section modulus. However, when you reach to mp, this is the time that this equation is not valid anymore. And you need to calculate the value of MP based on the area above and below your line. The moment that you reach to MP, again, the balance in the force is there. So that means the force that is generated in the compression zone equals to the force that is generated in the tension zone. So let's call this one P and this one F. So you know that this P is basically nothing but the area above the line, which is A over 2, let's say, multiplied by the stress sigma y that you have over there. And F also is the same, the area below the line, which is again A over 2, multiplied by sigma y. So if you equal these two, then you multiply them to the distance that they have from each other, then you can get MP. So basically this MP equals to A2 multiplied by sigma y, which is the force that you have, this force multiplied by the loading arm, which is from here to here, which equals to YC plus YT. So if you want to calculate the plastic modulus, you need to calculate first the plastic section modulus and then multiply it to sigma y. So MP basically equals to sigma pi multiplied by plastic modulus. Sometimes we show it with ZP. So this ZP is plastic modulus. For some sections, like if you have a rectangular section, we have a direct equation to calculate this Z or plastic modulus. If the width of your section is B and the height of your section is D, then the plastic modulus is 1 over 4 BD3. So you just need to know how much is the width, how much is the height, and you can get it. If you have a section with circular shape, then ZP can be calculated from this equation. However, if your section is not a symmetrical shape or shapes like the one that you see here, let's say you have a T shape, so in that case, you need to calculate ZP, and based on that, you can calculate MP. I will explain this one later, how we can get ZP, the plastic modulus, for sections like I or angle shape or T shape. So it is just following the principle that I explained here. That means we need to find a line that divides this section into two in such that the area above the line, which is A1, equals to the area below the line, which is A2. So this one very easily you can calculate. You can assume that this line is located at the height of Y, and then calculate the area above, calculate the area below, equal to each other, and get the Y. So this is the line that we call it line of equal area. It is not neutral axis anymore. Line of equal area. That means a line that above and below that line, the areas are the same. So after you calculate these, then you just need to multiply the area. You can need to calculate the moment of area of each area below and above the line. So you calculate this area, you multiply that area to its distance from center to the line that you have positioned in. And then another area, multiple to the distance between the centroid and the line of equal area. And then we have also plus another area here, multiple to its distance from the line of equal area. So from there, if you multiply all of them and get the total response, you can calculate how much is your ZP. I will solve an example to see this later. But the thing is, which is very important here, and we need to understand is the plastic modulus that you calculate and you multiply it to ZP gives you a bending moment that we call it plastic moment. Okay, and if you calculate the ratio of these plastic moment to yield moment, in which yield moment is the section modulus that deviated from uh, dividing of moment of inertia to c, which is the largest distance from the neutral axis to the fiber that you have here. So you have section modulus, you multiply it to sigma y, it gives you my. This is yield moment. So the ratio of MP, meaning plastic moment to yield moment, is a factor that we call it shape factor. This shape factor is very important because it's kind of showing the ductility of your section. The larger is this shape factor, the better is for the structure. Because if this shape factor is small, that means from the first yielding that occurs inside your structure until the complete yielding, which all fibers has reached to the yield, there is a small gap in distance. So if your structure is showing some crack, soon after it's going to collapse. That's the meaning of a small shape factor. But if you have a large shape factor, in that case, the moment that you see crack inside the structure, until the time that the structure comes to its large deflection and collapse, there is a large gap. So people can easily evacuate the building before it is completely collapsed. For your information, the rectangular sections have a shape factor of 1.5, which is much larger than I shape and C shape section, which is 1.155. That means if you have a beam, okay, you have a beam, one beam made of rectangular section and another beam made of I section, and you apply the force here, okay? Let's say both of them have the same MP. This one is MP, this one is MP, okay? You have designed them in such a way that both can generate, let's say, 100 kilonewton meter of bending resistance at the plastic production. So the moment that this one yields, okay, if it is a rectangular cross section, you have a large deflection, and if you have I shape, you have a small deflection. So this is the difference between these two. Almost 1.5 divided by 1.17, which is almost 1.4 times the larger deflection you will see for the rectangular section, which is very good for us. This way, we can understand that the structure is collapsing and we can leave the building. So now I want to introduce to you that how basically we can calculate the ultimate load of our structure when they are entering to the plastic zone. Okay, so we go through a very simple example, and this simple example is just a simply supported beam. Consider that we have a beam similar to this one, and we have a point load applied to it, P, okay? And under this load, we want to see the plastic condition and see what's happening. In other words, I want to know that when this beam is going to collapse, if I increase the P. Obviously, at the time of collapse, the force has reached to the critical load. This is P critical. That means if it is a little bit more than that, the complete collapse will be there. So P critical is the condition when we are going to have our plastic hinge form under the load, okay? So the moment that we have a plastic hinge formed here and the beam is in the verge of collapse, you are going to have a deflected shape like the one that you see here. Always we assume that the line that connects to our plastic hinges like this one are always linear, they're not bent, okay? So at the time of collapse, there's going to be some deflection at both sides of this beam. And also, we're going to have some rotation. So let's assume that the rotation is theta. And since the load is right in the middle of the span, the other side also is going to rotate theta. Okay? And from mathematics, we know that the rotation here equals to the summation of these two rotations. So theta plus theta is going to equal to 2 theta. And this 2 theta is basically rotation of the plastic hinge compared to the time that it was straight. So after you apply the load, deflection increases until it reaches the collapse. The moment that it collapses, compared to the original condition, it rotates 2 theta. This 2 theta is basically the rotation of the plastic hinge, and this theta are the rotation of the beam at the support. Okay, now I want to know how much is the critical load at the time of collapse. That means the critical condition is the condition that we have reached our bending moment to MP. In order to calculate that, we need to go through a technique that brings in calculation of internal work and external work. Okay, you know that from physics, work is force multiplied by displacement. That means if you have a box, you apply a force and you move it, let's say 10 centimeter. So this force, 10 kilonewton multiplied by 0.1 meter, is the work that you have done. So the same theory that we learned from physics, we can apply it to here. But here we have two types of work done. The work that is done by external force, which is this PC, and the work that has been done by internal plastic hinge that we have developed. So the force that comes from this PC is the force itself multiplied by the deflection that we have here, that we call it delta. So P multiplied by delta is basically the work that is done by the force, external force. But in order to calculate the work that is done by the plastic hinge, we should understand that if there is rotation inside our element that generates bending moment, the force out of that equals to moment multiplied by rotation. So this is also work, moment multiplied by rotation. Since the bending moment here and here, M equals to 0, right? So if M equals to 0 because they are pin support, that means there is no work done at these two locations. But in the middle, when we have plastic hinge, our bending moment has reached to MP, and our rotation equals to 2 theta. So we have MP multiplied by 2 theta as the internal work that is done by the plastic hinge. So this is what you see here as the internal work. The theory said always internal work equals to the external work. So that means this P multiplied by delta, which is the work done by the external force, should equal to MP multiplied by 2 theta. But before we equal these two, we can replace this delta by another parameter that makes our calculation easy. Since there is a rotation of theta here, from math, you know that L over 2, which is the length of this line from here to the middle, if you multiply it to theta, which is the rotation, that equals to delta. L over 2 multiplied by theta equals to this delta. It applies to any triangle that you have. L over 2 multiplied by theta equals to delta. So instead of delta here, down here, I can replace L over 2 multiplied by theta. So I can get P multiplied by L theta divided by 2. So this should equal to internal work. And if you do that, from there you can calculate this P. And since M equals to MP, P equals to P critical. And from there, you can see that the critical load equals to 4 MP divided by L. So what does it mean? That means that this beam can carry load until it reaches to 4 MP divided by L. So it depends on the length of the beam. The longer is the beam, the smaller is the force that it can carry. And the larger is your MP, the larger will be the force that it can carry. So let's assume that we have a beam with a cross-section of 0.2 to 0.4. Okay, let's say it is a triangle section, and the yield is 300 megapascal, let's assume. Okay, So let's say the length of your beam is also 10 meters. So for this section, you can easily, by referring to this equation, you can easily calculate how much force it can carry before it collapses. The first thing that you need to calculate is MP, and you know that MP equals to ZP multiplied by sigma y. So sigma y is given to us already 300, and we need to calculate ZP. And we know that ZP for rectangular cross section comes from this equation. So you can easily write down the ZP is 1/4 multiplied by B here is 0.1 multiplied by D, which is the height is 0.4, and it should be power 2. So from there, you can calculate how much is basically the value of plastic modulus. And if you get the plastic modulus, then you can multiply it to you can multiply it to sigma y and get MP. So MP is ZP multiplied by sigma y, and that is 0.04 multiplied by 300 multiplied by 10 power 6. So from there you can get how much is your MP. So if you got MP, you can put it inside this equation, and L is 10 meter. Then you can see how much is the critical load that this structure can carry. And your loads after imposing a safety factor should not exceed this value. Otherwise, it's going to collapse. So this is how we can design our beam for a point load which is applied to it safely without allowing to collapse. In this case that we investigated, the support conditions were both sides pin and roller. But in reality, we may face a condition that the beams are not anymore pin or roller. It might be a fixed condition. So we need to go through that condition. And for that cases, also, we need to calculate how much is going to be there, value of MP. So that is something that we are going to discuss it in our next class. I will solve more example like that in our next class to understand the case. But before we end our class, we need to also have few example about how we can calculate ZP for sections that are not rectangular. This way, if you have any type of section, then you can calculate its plastic modulus. Okay, so let's just go through one example and see how we can deal with this. Okay, let's say we have been given a beam with a cross section of T shape. And let's say from here to here is given to us 0.5, from here 0.2, and this is 0.4, and this one also is 0.2. So the question is asking calculate ZP or plastic modulus for this section. Okay, so the first thing that you need to do in the first step is to calculate location of line that provides equal area. So this is something that we need to go through it in the first step. You can assume it to be any place. Let's say I assume to be here, and from bottom to this line, which is the line of equal area, I assume to be y, the distance. So this is from here to here. So I need to see how much is y in the first step. So if I want to do that, what I need to do is to write down the equation that can give me the value of y. So we have one area here, another area on top, and let's say another area here at the bottom of the line. Okay, so I can write down, since the area on top should equal to the area on bottom, that means this area should equal to the area of the bottom, A1. Let's account that one, and let's say this one is A2. So A1 should equal to A2. So we use this equation to calculate y. So A1 itself, if you want to calculate it, is 0.5, okay, multiplied by 0.2. This is the rectangular on top, and then plus this small area that we have here. So for that area, we know that the width is 0.2, okay, but we don't know how much is the height, right? But we know from here to here is given to us 0.4, so we can consider it to be 0.4 minus y. So this is basically A1, the area above the line, okay? And then we have area below the line, which is A2. So for A2, we have 0.2 multiplied by y. 0.2 multiplied by y. So if you calculate this, let me calculate it for you. This way we can have a correct value. So 0.5 multiplied by 0.2, this is going to be 0.1. And if you multiply these two to each other, you have 0.2 multiplied by 0.4, 0.8. So you have 0.1 plus 0.08 minus 0.2y equals to 0.2y. So if you move this one, you have 0.4y equals to 0.18. And from there, you can calculate how much is the value of, so it equals to 45, if my calculation is not wrong. So that means it is coming almost, it is coming here. Okay, so we are here. If it is coming to that location, so this calculation that we have made need to be adjusted, because we have assumed in this calculation that the y is between area of this triangle, right? So right now that we have got 0.45, that means the area that is divided these two may not be similar. So we need to check again to see whether these two areas are correct, and the line has divided the section into two equal area or not. So right now, this is our section. The line has passed through here. So if we divided it into two parts, here is 0.45, and since the total height is 16, this one will be 0.5. And from here to here is 0.5, and the width also is given to us 0.2. So the area below the line is this area. So if you calculate that one, I call it A2. A2, so it's going to be 0.2 multiplied by 0.2 multiplied by 0.45, which is the rectangular below, and also we have 0.5 multiplied by almost 5, because this one becomes 0.5, 0.5. The height is 45, from here to here is 40, so that area becomes 0.5. So this one multiplied by 0.5. So if you calculate that, let me do it. So you can get 0.2 multiplied by 0.45 plus 0.5 multiplied by 0.005. So the area becomes 0.0925. So this is the area below. The area above, which is this area, it can be calculated easily. 0.5 multiplied by, the height is 0.2 minus 0.5. So if you calculate this, you have 0.5 multiplied by 0.2 minus 0.5. So you get 0.075. So you can see these two areas are not the same. And the reason is, in the beginning, we have assumed that the line will be within this triangle, but right now it is above the triangle. So this equation should be changed. And you need to again recalculate the position of that line of equal area. So bring it up here and do the calculation again to get the line of equal area. So what I'm going to do is to delete this calculation and run again my calculation, but this time assuming that the line is passing the upper side of the triangle, the rectangle. Any questions so far? Any question? Okay, so no question. Okay, so I delete this one. Okay. So let's go back to our calculation. So this time we assume that that line is passing here. So this is gonna be our y. You can assume it from down there, no problem. It's up to you. So from here to here is 0.4, 0.2, and obviously from here to here, this one also was given to us 0.2. So this is going to be 0.2 minus y. So again, we have the area above should equal to area below. So area above is 0.5 multiplied by 0.2 minus y, which is the height minus that area, should equal to 0.4 multiplied by 0.2 plus that small area up there, which is 0.5 multiplied by sorry, this one is, okay, I made a mistake. So this is going to be y only, because we assume that from here to here. So 0.5 multiplied by y is this area from above the line. And then we have 0.4 multiplied by 2, and then 0.5 multiplied by 0.2 minus y. This is 0.2 minus y, the area below the line. Okay? So here we have 0.5 y, and then let's calculate the other side. We have 0.4 multiplied by 0.2. It gives us 0.08. And then we have 0.1, and then we have negative 0.5 y. So if you move this one to the other side, you have 1y equals to basically 1.08. And then, so your y become basically 1.08. Did I calculate it correctly?
0.18.
Yes, that's correct. 0.18. Okay, so now this is going to be 0.18, and down there, basically we have 0.02. So this is going to be the line of equal area that we have. So let me just delete this very messy calculation and draw the section a little bit clean because we have the second stage of calculation over there. Okay. Okay, so right now we have our line. So this is going to be from here to here, 0.18. And down here we have 0.02. And from here to here, 0.4. And this is the line of equal area. That means right now the area above equals to the area below. So that was the first step, to calculate the line of area. Then the second step is to calculate the moment of area. So right now, if you want to calculate the P, you need to calculate the areas and multiply to the distance that the centroid of each one of them has compared to the line of equal area. So the area above the line, we have only one area, which is 0.5 multiplied by 0.18, okay? This is the area. And then multiple to this distance, we call it D here. So that D is nothing but 0.18 divided by 2 because it is in the centroid, okay? The height is 0.18 divided by 2 becomes centroid. So that is for the area above. Area below, we have two areas. So I divided into two. We have this area and this area. So for each one, you need to calculate separately. So we are going to have 0.4 multiplied by 0.2, and then multiple to the distance of centroid to the line of equal area, which is here. So here is 0.2, and then we have another, basically 2 centimeters. So it's going to be 0.22. This is 0.2 plus 0.02. So this is the distance from the line of equal area to the centroid. Okay, and then we have another area, which is this rectangular, this one. So the area of that one is 0.5 multiplied by 0.02. This is the area because the height is 0.2. And the distance between its centroid to that line also is 0.02 divided by 2. So you need to calculate this. This is going to give you ZP for cross sections that don't have is built from other sections. So if you have rectangular, it's very clear, 1/4b d power 2. But if it is I or T, step number 1 is to calculate line of equal area, the position, okay? And number 2, step number 2 is to multiply every area above and below, calculate the area, and multiply to the distance of centroid to the line of equal area. Sum it up, that can give you ZP. If you got ZP, then you can easily calculate NP for your section, which is ZP multiplied by sigma y. And this sigma y here is the yield strength of your material. Okay, so we will see one example in our next class that how we can do the calculation based on the values which is given in the question to us. Okay, so I think with that we can stop here. And we can continue more when we have our online class, face-to-face class. Any questions so far? Any question? Okay, if you don't have any question, I want to know who is in the class. So I will read your name. And please open your mic.
Doctor,
Yeah.
can you repeat the calculation of ZP?
Okay, it's been deleted. Why you didn't ask earlier? Okay, if you want to calculate ZP, do you see my slide?
No, doctor.
Okay, do you see my slide? Do you see the white page, the white page?
Yes, doctor.
Okay, the first thing that you need to do is to calculate ZP. okay, is to calculate the location of line of equal area. We don't know where it is, but this line of equal area divide the section into two parts. And the upper part and the lower part should have the same area. So let's assume this is A1, and let's assume all of these is A2. So this is line of equal area. That means the area above and below that line are the same. We don't know where is the location of this line of equal area. So we assume it to be Y from up or down part of the section, okay? So since the line of equal area divide this into two equal areas, so A1 should equal to A2. So from here, we can calculate the location of this Y. That means we multiple each one of these areas, we calculate them and we equal them. So right now below the line, we have only one area. So this is A1. But above the line, we have two areas, this one and this one. So we can divide each one and write it here. And these areas will be based on Y. And from there, you can get the location of Y, like the one that I did, okay? And then when you got Y, the second step is to multiple or to calculate the moment area. The area's moment compared to the line of area. So you come back here. Let's say right now you know where is the location of your line of moment equal area. So you calculate the area. This is the first area. You find the centroid. You multiply this area to the distance of centroid to the line of equal area. So let's say this is D1. Then you calculate the second area. Let's say this is A2. And the distance between the centroid to here, let's say this one is D2. Then you calculate the third area. This is A3. And then you multiply the centroid distance from the line of equal area, D3. So your ZP will equal to A1 multiplied by D1 plus A2 multiplied by D2 plus A3 multiplied by D3. So this is the ZP.
Okay, doctor, got it.
Got it? Okay.
Yeah.
Any other question? Okay, so if you don't have question, let me know who is in the class. I'll read your name, so please open your mic. Ang Kong.
Yes, doctor.
Okay. Ahmed Elsa.